Welcome back to the last portion of our discussion about logarithmic functions and equations. And in this video, we are going to talk about some application problems involving logarithms. So you may be asking yourself, oh my gosh, I don't know when I would ever use this. And yeah, you may be right. You may never ever use logarithms in real life. But there are lots of real-life applications of logarithms, so we are going to talk about a couple of them, all right? So one of these applications is actually the Richter scale, and I am sure that many of you have heard of the Richter scale. That is the scale we use to measure the intensity of earthquakes. And you've heard an earthquake hit Singapore with a magnitude of 5.2 on the Richter scale, or something along those lines. So there are various ways to calculate the magnitude of an earthquake on a Richter scale, but we are going to focus on this particular equation, which calculates magnitude by using here, magnitude is equal to 2/3 times the log of E over E naught. Now, E represents the amount of energy released in joules during an earthquake, and E naught represents the initial amount of energy, and that is going to be given as 10 raised to the 4.4 power joules. Okay, and then M will represent the magnitude, of course. So we could solve problems such as this. And if you're into seismology, this is right up your alley. What if 9.2 times 10 to the 12th joules of energy are released during an earthquake? How could we find the corresponding magnitude, rounding to the nearest tenth? Well, we're going to go ahead and use this equation and just sub in this 9.2 times 10 to the 12th for E and 10 raised to the 4.4 in for E naught. So let's go ahead and do that. And then we can just crunch this in our calculator. And when we do that, we get that the magnitude will be about 5.7 on the Richter scale. Okay, or we could have something along these lines. If an earthquake has a magnitude of 8.1 on the Richter scale, how much energy do we expect will be released? And in this case, we would substitute that 8.1 in, since it's the magnitude, for M. We know what E naught is. We know that that's 10 raised to the 4.4, and we'll be solving for E. So this is kind of the situation we have. Now, remember that if we're solving for E and we got all this stuff around E, we need to get rid of all the stuff. And we're going to work from the outside in. So let's multiply both sides of the equation by 3/2. And when we do that, we get 12.15 is equal to the log of E divided by 10 raised to the 4.4. I'm sorry. Notice we have a single log is equal to a constant. If we have the equation in that form, let's rewrite it in an exponential form. So we could say that that is the same as 10 raised to the 12.15 is equal to E over 10 raised to the 4.4. Okay, and so now if I want to isolate E, I'm just going to multiply both sides of this equation by 10 raised to the 4.4. We can take these two powers of 10, and since they both have a base of 10, we can just add the exponents, and we can say, well, E is going to be about 16.55 joules. Now, that seems like a lot of power, and in fact, you'd be right. It could cause some major damage. I don't know if it would tumble the Golden Gate Bridge, but we know that if it happened there, we could have a lot of problems going on. Let's look at one more application of a logarithmic function. All right, another application of logarithmic functions is found when we look at the pH scale. Now, any of you who have had chemistry or maybe even biology know that the pH scale is used to measure the acidic or basic nature of solutions. And another word for basic is alkaline. And we can find the pH of a substance by this equation. The pH is equal to the negative log of H plus. And in this equation, H plus is representing the molar hydrogen ion concentration. Okay, so let us take a look quickly at the pH scale just to refresh our memory about what does that look like. And remember that the pH scale ranges from 0 to 14. So those lower numbers are the most acidic values, and the higher numbers are the most alkaline or basic values. And then 7, right in the middle, is considered to be neutral, neither acidic nor basic. Okay, so we are interested in what is the pH of lemon juice that has a hydrogen ion concentration of 5.4 times 10 to the negative third power moles. Okay, so we are going to take this value and sub it in right here because that is where the hydrogen ion concentration goes. And then we are going to crunch these numbers to find the pH. Now, based on what you know about lemon juice, do you think that that's more acidic or more basic? So put that in your head and let's see if you were right when we get our answer. Let's go ahead and sub in that hydrogen ion concentration. And now I can rewrite this 5.4 times 10 to the negative third in a value that I can kind of understand a little bit better. That is 0.0054. And I want to take the log of that. Log of 0.0054 is negative 2.27. And remember, I've got this negative in front of this, so I'm going to take a negative of this negative, and I'm going to find that the pH is about 2.27. So about here on the pH scale. Well, you may recall that lemons are full of citric acid, and so we would expect that lemons would be on the acidic end of the pH scale. So we might want to just look at different items and at where they fall on the pH scale. And this is just for your information and interest. And if you're not interested, that's quite all right. We're going to go ahead and say that we're about done with applications. But I want to remind you that if you are given some lemons or lemon juice, the best thing to do would be to make some lemonade. And with that, we will conclude logarithms, and I will see you next time.